Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk.
Hey.
We were just chatting, catching up, kind of our chit-chat type stuff. And, I'm getting better. We've been doing this for a while, and I'm actually saying, wait a sec. Let me hit record. Because this is what
As soon as we hit on a sensitive subject and something that we may have different opinions about, yes.
Yeah, then I
agree. Then we say, okay, we can have a discussion about this subject. And,
that's right. If we're in violent agreement, it's not as fun. Yeah.
And I think you just said the big question that we want to discuss today is reliability more than just testing?
Yes. And it came up as what should a reliability engineer do? And it is in the context of say you're in an early phase of development and you don't even have prototypes yet. I mean,
right.
And your comment was they would be bored. I'm like, no, I think there's a lot they should be doing and can be doing that will actually improve or influence the reliability performance. And I think that's where I said, oh, wait a minute. We got to hit record here.
Oh, I do believe there is more to reliability than testing. And in fact, a lot of reliability is planning the testing and planning and building the fixtures and building the test equipment before you may have the materials. And
that's still testing. That's all still testing.
Okay. That understanding the material properties, talking to the vendor. There can be a lot of upfront work, but yes, it's the goal for me would to get good test scenarios or effective test scenarios that show you something useful or relevant to its strength of the product or the strength of the mechanism or the wear of a mechanism or whatever you're anticipating will be the degradation mechanism that could lead to a failure in time. So, but I'm not real keen on, and as you've known, I've talked about models and doing predictions and doing estimates and doing things like that based on, past book data or, proposed mechanisms or whatever, because I feel as can be, and as, I have the article on my website, reliability prediction, continued reliance on a misleading approach. And that is the problem, that sometimes the prediction or believing in that predictions can mislead you to do the wrong kind of testing or
just not even do testing. Oh, we're good.
Do wrong. You just
making bad decisions.
Do things that are not as relevant as understanding the product. And, every time, so like a company, a supplier gives a specification for the product, okay, or for their material component. Or something, a component or something like that. He generally doesn't know your exact application or your end-use conditions or how long you're going to be at any condition, and generally companies that are designing new products don't say a lot. They don't want to, have somebody reverse engineer or know that you're developing this, new technology or new.
Yeah, I heard that last year. I heard it. It was this. They called me to he asked a few questions to see if I was interested in a project, and they says, "Well, what do you do?" And he says, "Well, we can't tell you. We're in stealth mode." I'm thinking to myself, in other words, you don't know what you're doing. Which might have been true.
It could be. And so it's a nice way of saying it as well. We can't tell you.
That's right.
And then you find out they really don't have a clue. Maybe.
Yeah.
Or they're really struggling at the beginnings of their efforts. But
just trying to figure out what product to make. But the idea is I agree. You and I totally agree that, parts count predictions and total reliance on those kinds of things is folly. Now, I think there's a gradation, though.
But any reliance. I mean, a
not
lot of
any.
reliance.
No, there are some.
There are some that are useful. It's like you said.
but it's really down to the failure mechanism. And I think that's
Right.
where you and I come together, is they say, you
Right.
really need to understand the failure mechanism. And if
Right.
you are making something that's using sack solder and all your assessment, you just want to know, is, will this work in our environment? The
Right.
thermal cycling that we're doing and vibration we're doing. There's plenty of papers out there on that, and all kinds of scenarios. And if you get the process right, you inform the joints properly, all those kinds of things. And you can go test those and check those out and make sure your suppliers are doing it right.
Right.
There's models to say, yeah, this will last X number of years or cycles for this
Right.
application. I actually had one team that asked me about using this kind of solder for a satellite in a low Earth orbit. And it circled the Earth, I don't know, a gazillion times a day. And it went from the dark side to the light side. And it had like 120 or 150 degree C temperature change from when it was in the sun, when it wasn't. And and they're asking me how to do an accelerated test on it. I says, well, just fly one of these satellites. You're getting better conditions than we could ever get on the ground. So they were kind of, maybe we shouldn't use the solder, because if we can break it in 6 months in the lab in conditions that are less than what we're seeing in the field.
Right.
It's like, you might want to rethink that. NASA's got a lot of stuff on this about, what you need to do. It's like, all right.
Well, they have a lot of experience, right?
Yeah, exactly. So let's go to those guys, see what they're doing.
And, I just posted an article about how the new helicopter Ingenuity found some limits of its ability to transmit its signal to I think it's Endeavour. No,
the rover, whatever it is.
Perseverance. Yeah. The rover.
Was this the picture where it was climbing a cliff or something like that?
Well, the helicopter went off in a place where there was a hill between the Perseverance and the rover.
Well, there's not a lot of atmosphere to bounce a signal.
Right. And in fact, the Ingenuity, I believe, flies very low in general to the ground, maybe a few meters up above. But anyway, it was low enough where there was interference of the signal on the hill. And Ingenuity lost its contact with Perseverance. But, of course, it's been designed that if it does that, it comes into a mode of powering down safely and landing safely, hopefully, and looking for flat area ground. I don't know how much automation, but it's quite a sophisticated helicopter to be doing all of its stuff autonomously, because we can't real time have anything really controlling it from Earth. So it's pretty amazing technology. But yeah, those kinds of things, they would know what the cycle time, cycles on Mars are, and look for, those extreme conditions that don't exist on Earth as far as thermal cycling. And would, I believe, to accelerate the mechanisms of expansion contraction in those harsh thermal cycling environments that exist in space, they would go well beyond. They would first find out where the limits of that reflow or solder capability is temperature-wise, and then start cycling well beyond, hopefully significantly beyond what it will experience in its real environment.
Yeah, and there's limits to that, though. We could do a whole episode just about how do you set up a test and sort these things out. But I think the key point there is that it's that there is a shift from learning about, what do you think is going to fail? And FMEA is a good tool for that. And just engineering judgment going, we're not too sure about this or that, as you learn more about the environment and all the other stuff. Right. Now, I can see, if you squint at the paper hard enough and on the edge, that's test planning, right? But out of the 10 different failure mechanisms we run across, we don't have the resources to test all 10 of them. So we're going to look at the one we know the least about, or the one that we think is going to be the most likely to cause a limit, and then we have to decide to do something different. So we need to know that answer sooner than later. So that's where I then shift into into that test. Because it could be, if I'm making something that we've made gazillions of them before,
Right.
and we've got a stable process and we're going into the same environment, right? I'm just changing the color of the case on it, for example. I really don't need to do a whole bunch of testing.
No.
You know, I already know the story here. It's working. It's good. Don't mess it up and ship it.
But if you're changing an IC or a circuit board, there's another whole possible scenario that you want to test for based on your actual previous design and what it was capable of. You should be at least capable of the same kinds of margins and strength that you had in the previous design.
The testing's expensive. So even HALT is expensive. And there are cases in my mind that running a test has got to have a clear purpose. And so if I already have a Pareto from field failures and we're doing a cost reduction or a process improvement or something, then, and I could recheck the margins or change, but if I have something that's obvious and I already know what the failure mechanisms are and I know what the fix is and the supplier is running that test for me, I don't have to. I'm done. I ship it. Whereas if I don't have a Pareto of a bunch of issues to go solve, well, then HALT is a great tool to populate that. Just go figure out what's going on and where the mechanisms are.
I agree. And HALT is not always expensive. It actually is not. I mean,
it's not compared to other things. Yeah, it's
voltage margining is not expensive. I mean,
not
in general. Okay, you're talking about the full blown chamber and thermal cycling and combined environments, which yes, that's what traditionally people think of a HALT, but I just think of changing the weight, just like Boeing does when they finally fatigue a wing by bending it until it breaks.
Yep.
Okay. And they do that, even though it's a quite inexpensive test. But they get so much information, they instrument it up significantly more than they could in the in-use environment. Yeah. They do a lot of computer monitoring, and they know a lot of details about the physics of the stresses and everything once they break it. But they actually do break it. They don't rely on a model. They say, okay, let's see where it'll
prove
crack.
Our model out. Yeah. No, I totally agree.
It proves their model. So. Right. So that's not necessarily to, we talk about limit testing or finding operational destruct limits, and that's kind of it, or it's so far beyond the fundamental limit of technology that you worry about.
You got to really do something different. Yeah.
Yeah. You can.
So what I'm getting at though is that if you're starting a program, right, at some point you doing testing, whether it's on the bench with the engineers to see where your limits are, or how does it respond, or what happens if this kind of phenomena occurs, or, what if we get a variation from a supplier, or what, all of those kinds of things, I think to a large extent occur pretty naturally with most engineers. They're pretty curious. Does this thing work? And what happens if this happens? Kind of that kind of stuff. That's all part of reliability. I have no doubt in my mind that it is. And doing accelerated life testing or HALT or more involved, types of what we typically call reliability testing or environmental testing, those things are part of the picture. Yet I don't think that is reliability engineering. I don't think that's the sole part of it. Now, we do agree that doing parts count prediction and calculating MTBF in your sleep is just not worthwhile. Don't do that. But there's a whole nother realm though of setting up the organization and setting up the thought process and creating guidelines and creating systems to track failures until they get resolved, understanding what's the use environment and characterizing that. Those are not testing, right, necessarily, but they are
not necessarily, but they're part of the reliability planning and testing path. Now, you talk about certainly failure tracking in the field and things like that, which is certainly a part of your overall feedback of reliability. I mean, most critical.
I know where you're going with this, because part of failure, correction activity, fracas type systems or corrective action is to test to make sure that it works. You have an actual fix and that it really does work. So, yeah, we do a lot of testing. I don't think that's all of it though. it's FMEAs, it's risk analysis, it's environmental considerations and understanding failure mechanisms from those realms. Yeah, we talk a lot about failures in one sort or another. And it's really, really useful to have a picture of it in the lab that you can replicate. That's really powerful. But we don't always get that opportunity. And I think what we miss by focusing on testing is that we need to focus on the culture in the organization so people think about reliability and actually, hey, I'm building a new wing. Do you think we actually might need it to work? I'm being facetious there, but the idea is that vast majority of how a product achieves its reliability goal is not the reliability engineer. It's due to the design and engineers and manufacturing engineers and the management teams making decisions. And if we influence those, then we have much more leverage than heading off to the lab to tinker.
Well, right. If we address those with real data, either facts about the materials or facts about the
environment, the conditions, what we know and don't know about stuff. Yeah.
I guess, Fred, I look at it as overall in the umbrella of goal. The ultimate goal is getting to an effective, useful, and most informative testing that you can develop for that. Yes, it's all before and FMEAs, that's not directly testing, but that helps you give a better idea of what to test for and what to test and what the significance of each subsystem might be. So,
but FMEA output is not only for testing. It supports
not only for testing.
There's other things we do that come out of FMEAs that has nothing to do with testing. And so it might become apparent that, hey, we need a redundant design here because this single point failure is not tenable. We won't achieve our goal, or, just basic stuff and risks that we face that we don't need a test to solve it.
You're right. And I gave an example of a respiratory gas analyzer, and it wasn't anything to do with the testing that instigated it.
But that was the one you were talking about. It you've got this high concentration of oxygen, and you have this really hot thing in there. That might not be what's the by the way, I was just thinking, just walking down the hall, what's the ignition flashpoint for oxygen?
So, in the gas analyzer, it initiated a change in design that was nothing to do with it. Nobody tested it. It basically was a mechanism that needed to be addressed in the fact that it was a single point failure. Just like, unfortunately, the Boeing 737 MAX and the single point of the angle attack.
The angle of attack, I think it's called. But the idea, though, is that I think sometimes it's what questions we ask and what things we ponder about. And sometimes we get dangerous with that, going, it'll never work. And let's be specific. And I think your point of what's the data, what's our understanding of materials and properties and all these other things.
Right.
Some of it is setting up
the time.
What I think,
not 20 years from 20 years ago.
No. What I'm thinking is that part of it is setting up one is being the example of saying, well, that's a single point failure. What happens if that fractures?
Right.
What happens if? But setting that up across the organization so that it becomes a natural part of the design process. Now, you're successful is when the design team comes to you and says, hey, we're thinking about doing this. And I had one of them, they were going to put a circuit board on an edge connector standing vertically. And it was about an 8-inch long, think of it as a diving board, just kind of standing straight up in the middle of this device.
Yeah.
Good. And it was a inkjet printer. So it has this big print head thing, is when the ink was on the print head. So there's a bunch of mass there going back and forth. And one of the problems with these early inkjet printers is they would vibrate enough to walk right off the table. And so it doesn't take a mechanical engineer to look at that design and go, you're going to wave this circuit board, only attached at its base. And the mass is perpendicular to this. That's going back and forth. Ding, 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 ding. I said, now, I may be mistaken, but I don't think that's a good idea because circuit boards don't like flexing.
Yeah, that's right.
And nobody believed me. So this is one where I, ran off down to the lab, and we had just gotten a high-speed camera. So we took the skins off, we fired this thing up, and we saw the part coming off the circuit board. We saw the shape of the bending. It was really exotic. And when it really started printing a full page color, it just ripping back and forth this big mass. And it was like it had two different nodes of bend inflection on it. It wasn't just a dive board going back and forth the whole length of it. It was a exotic S-shaped thing. It was way cool. And then we saw this part flying off of it. So I didn't have to write a report.
How long did that take?
About 30 seconds. No, it was 30 seconds.
Accelerated testing. You did
I just turned it on.
Real-time in-use environment.
Yeah. And I showed the little video to the mechanical engineer, and the next day they had a solution.
Right. But no argument there.
No, it was a demonstration of the problem. Was that a test? Yeah. I said, well, let's go see if it fails. And I was we were going to do a little pool. We were joking. It's like, how long will it take? And all that stuff. And we didn't do it. I would have lost. I thought it'd last, 2 minutes.
Well, those are easy. I mean, those are the easy ones to get the engineer. If you're running under use conditions and it fails, without any acceleration to it, hey, no argument there. This is what it's going to use in its in-use environment. The problem comes when you talk about trying to accelerate things and then going beyond the stresses that it'll see in its in-use environment. And when things break, then arguing that could occur over time, from not time zero, but in some.
Well, that's easy.
Quantifying that time is another thing.
That's a whole different issue. But
right.
But I think, we've talked about it many times. Is the approach of HALT is we'll find out what will fail. What's going to be a problem early on. And in some organizations, they actually need a demo, right? Let's take an existing product that's been in the field. We got a big history from field failures and failure analysis reports. What would you find if you did a HALT on that? Would you find all the stuff that we see in the field? Right. And 9 times out of 10, you find 8 of the 10 things, the top hitters in the field.
Right.
I think if you would have fixed that, you would have $800,000 in the bank.
Exactly.
Instead of paying for failures.
The way of selling the process or showing the benefits of the process of going to limits, testing to limits or testing well outside the end use environment. So that's what, is it relevant? Yeah. Here's all these things that we saw in the field, and here's what we saw in the chamber. And 8 out of 10 match what we saw in the field. So it's probably relevant, and you probably should fix it as opposed to betting that it's not and finding that out later.
Wishful thinking doesn't work as well.
Yeah. So that's when you have had a history of a product or a similar predecessor product, you've got it a whole lot easier than coming up with a totally new design that you've never produced and you've not any field data from. So they definitely take different approaches. And you have different data to support what you're going to be doing. And so I'd say from a beginning of a startup or a company that doesn't have a product in the field, it becomes a much more challenging, especially if people haven't been exposed to limit testing or strength testing or stress strength, comparisons or things like that, which is, again, I try to get away from this HALT, and everybody's immediately thinks of a chamber. Just think of boundaries and testing so that you find where you're how much margin boundaries you have between stress and strength. And some you won't find anything. And I've had HALT tests where the only point of failure is where it becomes irrelevant, like the solder reflows, or the plastic housing melts or the fan melts or something like that. And if you don't have a weakness that you do a HALT test and you have as much margin as the fundamental limit of technology really allows, which is the standard materials and methods. If you have that much room, then that with this fundamental limit technology margin, you have a lot more capability to stress it to accelerate it, to time compress.
Do all the other things you need to do. We've gone over that a bunch of times.
Right.
So one last thing that's a reliability engineer's role that, well, you can guess it's kind of related to testing. So if you find all these cool margins, right, it's way capable, right? Your number one job is don't tell the marketing people.
That's right. That's absolutely right. Oh, yeah. We've tested it to that level. Yeah. It did fail at 145C.
You can do that all day long. It'd be fine. No, let's back up here, guys. Let's back up here. Yeah. So, I mean, there's lots of stuff we do in reliability engineering. We deal with finance. We deal with marketing. We deal with the manufacturers, with suppliers, with customers. We do all kinds. We can get involved with lots and lots of different things. And having data, having hard evidence is a great way to influence a team. So I think
it's the only way to influence a team.
Well, there are other ways. Well, we got to talk about this.
All right.
We got to talk about that some other day. So
that's the most effective way of influencing a team.
Well, we got to talk about that.
Okay.
So I mean, if you're listening to this and is reliability just testing, or is there other techniques and methods and stuff that can get to a reliable product where you don't always focus on testing? And I don't think it's either or. I think there's a blending of these things. It's testing in its many, many different forms is one of the tools that we use, and we often do. And so I don't think there's anything wrong with that. I don't think it's the only thing we do. And that was my main point. So if you agree or don't agree with me, Kirk and I think we agree by and large most of the time.
We agree most of the time. And I believe what we're talking about is before testing is possible, then planning. And that's, to me, all of it's focused towards that direction, understanding the materials system, the in-use environments, all of that is part of going down the road to getting to eventually test the product. Yeah. And you're right, it's expensive. So doing testing most effectively and with relevance to the end use conditions or the end use risk is really part of the process that is all, final goal to me is to get to a point of an effective test and especially a strength limit test.
Yep. So
that's it.
If you agree one way or the other, or have another point of view you'd like to chime in on, you can do that. You can let us know. You can record a voice message to us over at accendoreliability.com/go/SOR. And we have a SpeakPipe widget, which is basically a browser-based voicemail. And you can record us a message, and we'd love to hear from you. Or you can write us a note or a comment there, or you can find Kirk or I or the other hosts of the show on LinkedIn or on our About pages. Lots of ways for you to join the conversation. And now I got to remember the 6 different topics I want to talk to you about, Kirk. So I should have been taking notes.
Fred, haven't we talked about everything yet?
No, definitely not. I don't think so.
Okay.
Well, we'll talk to you again real soon, Kirk.
Okay,
Take
Fred.
care.
Good to talk to you. Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.